Hi everyone, this is Lee here. In this video, we're going to go over potential energy and forces. Let's begin. So, to start off with this topic of potential energy, we have to go over this idea called a conservative force. Alright, so this term will come up a lot for our course. Now, I'm going to give you the simple go-to definition for what we can use in class to really help us define what a conservative force is. So, a conservative force, by all the definition, we can just say it keeps the mechanical energy constant. Alright, now you saw that I wrote ME here, so let's define what ME is. ME is what we call mechanical energy. Mechanical energy is a combination of energy. So mechanical energy is any kind of energy that describes an object's physical motion. And what we can use is that mechanical energy comprises of kinetic energy and potential energy. And that's today's big topic, potential energy. We use the variable U for potential energy. So kinetic energy, kinetic plus potential is mechanical energy. Now, I implore you to memorize this. This will make our lives so much easier whenever we are talking about anything that deals with energy. Alright, so conservative forces are any force that keeps the mechanical energy constant. Another way to think about this is any and all potential energy sources are from conservative forces. Okay, and I'll give you a list. We have F of G. Okay, this is the weight or the force of gravity. Is a conservative force. The gravitational force is a conservative force, and the next one is the force of a spring. Okay, so all three of these forces lead to some form of potential energy, and they are all conservative forces. Here are a couple that are not conservative forces: force of friction and air resistance. So friction and air resistance are not conservative forces, and any forces on the left are conservative forces. Now, the one last definition that I'm going to use to describe conservative forces is like a way to really summarize this concept in your heads. Okay, so the important thing about conservative forces is it is the idea that the path does not matter. Okay, only initial and final matters. Okay, final, I guess, position. It is path independent. So what does this mean for us? If you remember, when we're talking about the gravitational force, right? We said the gravitational force of, let's say, the Earth and the Moon. Right? So here's our Earth and here's our Moon. Now, here, the Earth and the Moon, they are separated by a distance, r. Okay, and it doesn't matter if the Moon is here at the location or if it's orbiting around. It doesn't matter if it's there in the location, or if it doesn't matter if it's here in location, right? Because the distance is the same. Well, the orbital distance, well, technically it's not, it's more of an ellipse, but, you know, for our example, right, the distance away from the Earth is always going to be the same. So only the starting location, which is the Earth, and the final location, which is wherever the Moon is at a distance of r away, that's the only thing that matters, okay? Only that physical distance. Another way to think about it is we're about to go into the definition of gravitational potential energy. But I'm going to use a little example first, all right? So if I have a table here, right, and I want to move my, let's say I have a red ball. I have a red ball right here. And my job is to move this red ball from its starting position here, and I want to put the red ball up here on the table. Okay, so that would be XF. Now, it will be easy for me to just get this red ball and to move it along, right? To just pick it up and to move it right there. That's one path. Another path I can do is I could pick up the red ball straight up and move it to the table, to my location. Another path that I could do is I could move this red ball along the path, raise it up, and then move it over. Okay, so these are different paths. And once again, conservative forces, the path does not matter, only the starting location and the final location. And for the last example, we're going to go a little crazy. Okay, so I can take this ball right here, I can bring it up here, I can swirl around, right, go all over the place, right, I'm moving all over the place. Okay, it doesn't matter, I'm going all over the room, but if I end up right here, that crazy journey didn't matter. Only the starting location and the final location, that's the only thing that actually matters when we're talking about conservative forces. Now, non-conservative forces, the path does matter. So what this means is, let's get rid of this crazy path, right? So if I'm saying the path does matter, let's think about air resistance. All right, so when you move an object through the air, we're actually moving the air molecules out of the way, and that generates kinetic energy in the air molecules, right? You're giving the air molecules energy. And so if we take the shortest path, which let's just say is this path I'm about to draw in, right? This first path, this is the shortest path, let's say. Okay, so if that's the shortest path, then that means that I had less time for my interaction with the air molecules. And so because of that, I will say this is journey number 1. In journey 1, the air resistance is pretty low. All right. Now, what about journey 2? So we'll say this is journey 2. I'll make this a little bit bolder for us. Right. I moved up, and then I moved to the right. All right. So in journey 2, my air resistance, it went up a little bit. Okay, it's not the lowest, and it's because I took a longer path. So the longer my path, the longer I had time to interact with the air resistance. And what about journey 3? Journey 3, I had the longest journey. So because it's the longest journey, I had the most amount of time to interact with the air molecules. So for journey 3, my air resistance was the greatest. And so because the path actually matters for my air resistance interaction, we say that air resistance is not a conservative force. Okay, because the path matters. If the path does not matter, we say it's a conservative force. All right. And an easy way to memorize this is that any type of potential energy comes from a conservative force. All right. So let's go into the actual equations for potential energy. So like I said before, potential energy, the variable is U, okay? And there's usually a subscript. So if we say U sub G, this is gravitational potential energy, okay? If we say U sub S, this is the spring potential energy. Okay, so that subscript, it helps describes what type of potential energy we're talking about. All right, now the formula for potential energy, and you're going to enjoy this if you enjoy doing some math magic here. So we're going to start off with the equation for mechanical energy. Now, if you remember, mechanical energy consists of two types of energy, kinetic energy and potential energy. And so, according to the law of conservation of energy, however change you have in any of those energy, as long as there's no outside forces, it has to be 0. So we can say that our change in kinetic energy, okay, plus our change in potential energy, as long as there are no outside forces, has to be 0, right? So the energy can't change. The total energy, the total mechanical energy, it cannot change. Now, this is very important. So we're going to start off there. And this is a formula that we will revisit later on. But to come up with the overall formula, this is a good place to start. All right, let's follow along. So what I'm going to do is I'm going to move my, my delta U to the other side. So I get delta KE is equal to negative change in potential energy. Now, if you remember from the previous lesson, we said that the change in kinetic energy is actually work. So I'm going to write that formula off to my right. Work is the change in kinetic energy. So I'm going to substitute in my delta KE with W, my work. So work is equal to the change in of the negative potential energy. Notice it looks a lot like the formula above, except there's a negative. And there's a very important reason for that negative, and we'll get into that in a little bit. Okay? All right, so after that, we can do a little bit of our math stuff. We also said that work is equal to the integral of f dot dx. So we're going to put that in there. The integral of f dot dx is equal to the negative delta u. All right? And from here, I'm going to just expand out my right-hand side a little bit. We can say negative, okay, u final minus u initial. All right. Now we're gonna do a little bit of our hand waving up in here to get the calculus that we want. We're going to get rid of the integral. Okay, and we're going to do that by taking the derivative of the entire line. So we're going to take the derivative of this entire line, but we're going to be able to do this by, with a very special thing, this is where the hand waving comes in, we're going to say that our u initial is a constant. So what that means for us is whenever we approach an idea in physics, we used to say the initial position is something that it doesn't change for the situation. We can always make our u initial 0, right? Our u final might be different, but our u initial, we can always claim it to be 0, and everything just shifts according. So we can say that u initial is constant. And so what our formula turns out to be, okay, f dot dx is u final, right? I'm just going to make that 0. And so we're going to take the derivative of the entire line. Now when we take the derivative of the entire line, we're going to get rid of that integral. All right? We got f dot dx is equal to negative du, because we just took the integral or the derivative of u. All right. So from there, we can find that force is equal to negative du divided by dx. Okay, so what this tells us is that the change, the minute change in potential energy over the change in position gives us the force. I'm going to put a negative there. Now, what that means, okay, what this means, and we're going to go into what this negative means, is that this idea of potential energy, okay, this is what is describing nature. This says that if objects are left alone to do their thing in the universe, it will always seek out this right here, this clause, this statement. Okay, so I'm going to use my example for you. If we have, let's do a table again, right? If we have a table, and on that table, let's say we have a ball, right? We have this green ball, and if we were to, let's say, slightly bump the table, okay, so that the ball is moving to the right, okay. Over a period of time, this ball is rolling to the right, the ball is rolling to the right, until the ball is no longer touching the table. And this is important here, because this is where we have to use our imagination a little bit. The ball is no longer touching the table. So at this point, the universe is going to follow this rule. The universe is saying the system will always seek out the lowest form of the potential energy. Okay? Where is potential energy the lowest? And for this case here, it's just going to follow what it naturally wants to do. And so I don't even have to tell you what the equation for potential energy is. If I were to ask you, if the ball is not touching the table, what's it going to do? And the answer is, the ball is going to fall to the floor. The ball will fall to the floor, and the ball will land on the floor, and over a great period of time, the ball will just stay on the floor. So what this tells us is that up here, we have a potential energy that is high, and here we have a potential energy that is low. And what the universe always wants to do is go to a lower state of potential energy, no matter what. Okay, it always wants to go for a lower state of potential energy, no matter what. Now, this is an example of gravitational potential energy. Another example of this, once again, we didn't go into the equations yet, but when we do go into the equations, this will, we can apply numbers to it. If we have a spring, and let's say we were to stretch out the spring, Okay, stretch out the spring, and when you were to let it go, what nature wants to do is the spring will want to spring back. It wants to go back to its original, like, compressed state, right? It doesn't want to be stretched out. That's normal. What is abnormal is if you stretch a spring and you let it go, the spring becomes even more stretched. That's abnormal. The universe does not like that. And so what this tells us is that when you stretch out the spring, that is high potential energy, and when you let it go, when it goes back to its more of a compressed state, that is a low potential energy. Okay? And so what this force is telling you is that in order for the objects in the universe to go back to its lower potential energy, whatever force is acting on the object will make it go to that lower potential energy. Okay, it'll always go against the where it currently is. Okay, and that's where that wonderful, beautiful, and negative comes from. It's really cool way that the universe works. All right. Now with that, let's come up with your equations for gravitational potential energy and for gravitational spring potential. No, excuse me, spring potential energy. So let's do UG first. All right. Now, I want to first start off with the formula for potential energy gravitational is mg delta y. Okay. Well, delta y is a change in height, and so sometimes you might see me write it as mgh. Okay, or even mg delta h. So these are all forms of potential energy. So what we want to do is we want to be able to derive this, right? We want to be able to come to that formula using the calculus from before. Let's try it. So let's say we have an object, right, and it's above the Earth. Let's say it is at a height of h, okay, and we release this ball. So when we release the ball, nature will take hold, the universe will do its thing, and this ball will fall to the floor, right? And let's say it hits the floor. So we can call that a height of 0. All right, so let's set up our calculus. So I am here to tell you that u is equal to negative f dot dx, okay? Or we can even say f dot dr. Yeah, I'll do f dot dr because we're using the y-axis, right? F dot dr. Okay, so let's set our constraints. Our starting height is 0. No, excuse me, our final height is 0, and our starting height is h. Okay? All right, next line. Our force that will be pulling on this object will be the force of gravity, and we know that force of gravity is equal to m times g, so we'll put that in there, m times g dot dr, okay, and we will integrate this. Now, at this point, you have to take a look at the integral, and you have to ask yourself, what are my constants? Okay, and the best way to do this is to take a look at that and your constraints. Okay, so the three things that are highlighted are all linked together. That dr is describing your starting and your final positions. Okay, and I'm going to use the word positions here with a lot of emphasis because only the positions can be integrated. Anything else is considered to be a constant. So here, mass, is mass a position? It is not. It's considered to be a constant. So I'm going to bring that out. Deceleration to gravity, is that a position? No, it is not. So I'm going to bring that out. All right, so we have that, and then we still have our integral. We didn't do any integration yet. So with that, what we can do is now we can actually integrate it. We say negative mg. So if we integrate dr, right, we get the integral of dr is just r, and we went from 0 to h. All right. So we have negative mg, r final minus r initial, if we're going from 0 to h, and we get negative mg h minus mg times 0. And mg times 0 just gets us 0, so we get mgh. So potential energy here, we got it. We got mgh. Now that negative just means that the force of gravity will be pulling it down, and so if we were to take a look at the magnitude, right, the magnitude of it, we would just say is mgh. Now, cool thing to do is within the original problem, right? If we said our force of gravity, it's initially going downwards, right? Because that direction does matter. That negative will also cancel out, making everything else to be a positive in the end. Right? So we did it. We found the gravitational potential energy equation using our calculus. All right. So this is used to describe any object that is above a height of h. Now let's find the potential spring equation. All right. So for the potential spring equation, I have to first give you the force of a spring equation. So F of S is equal to negative kx. Now what this negative tells us is that it's describing the nature of the spring. So this negative just means the opposite. So what this means is that if you push on the spring, what will the spring do? And that's what the negative is describing. The spring pushes back. Okay, so if you push on the spring, the spring will push back. So for example, if I push the spring to the left, right, so this is me, the spring will push back to the right. Spring. If I pull on the spring, right, the spring will pull back in the opposite direction. So that's what that negative means. All right. Now, if we were to find the potential energy of a spring, right, we got to use the potential energy formula is equal to negative the integral of f dot dr. Okay. And let's find our constraints. To find the constraints, I'm going to start off with a quick little sketch. So let's imagine that we have a spring that is horizontal, okay, and this is its initial state. All right, this is when we don't stretch it at all. It's right here. And so at that state, we can call that x is equal to 0 meters. And the cool thing about a spring is that it doesn't matter if you stretch it or if you pull it, the x is actually an absolute value, and so the force will remain the same. So what I'm going to do is it helps me if I draw it, if I sketch it, okay. I'm going to stretch it out to a distance of x. So this is x final, and we'll call that x. Okay. So we don't know how much we stretched it, but we stretched it with a distance of x. So our initial, we're starting off at position 0, and then we stretched it to position x. Okay, so I'm going to do the same strategy again. I'm going to put in my force of the spring equation, which is negative kx dot dr, right? That r is standing for position. And at this moment, I want to identify within my integral what I'm actually integrating. So this dr is talking about the position, because my constraints are the location of the spring. Okay, so between k and x, k is what we call the spring constant. So I'm going to write that down over here. K is spring constant. So what that tells us is how stiff a spring is or how flimsy a spring is. So a like car shocks, right? The thing that prevents the bouncing motion of a car, it has a high K. Okay, it's super hard to pull that apart. Versus like a slinky, right? Or maybe even a rubber band, easy to stretch, low K. Okay. All right. So K is describing the spring, the physical spring itself. It is not a position. And X is how far you stretch that spring. So it's talking about position, right? So notice how I'm highlighting it. So everything that is highlighted can be integrated. Everything else is a constant. So I'm going to pull out my negative K, and we're going to integrate it from 0 to X, where it's negative X dr. Okay, now I'm going to do some hand waving here. And I'm going to clean this up a little bit to make it look a little bit better for us, right? So negative times negative gives us positive k. We're going from 0 to whatever that final stretch x is, and we are, oops, took out that negative, so that should be negative there. So we get x dr, right? And that r is just describing the position. Okay? Alright, so if I were to integrate this, I'm going to raise my exponent up by 1, so 1 plus 1 is 2, so it'll be 2, and then we get to divide it by that from 0 to x. So we get kx squared divided by 2 minus k0 squared divided by 2, and of course this turns out to be 0. So what we're left with is u sub s is equal to 1/2 kx squared, where k is the spring constant and where x is the displacement, so either the push or the pull. And because this is squared, it doesn't matter if you push it or you pull it, the amount of energy, as long as the compression or the stretch is the same, it'll be the same potential energy. Okay? And so we just derived the spring potential energy equation. Isn't that cool? I think that's pretty cool. Alright, so the very last thing that I want to talk to you about is the equation for force, right? So we left off with F is equal to negative du over dx. Now, if you remember, whenever we take the derivative of something, we're looking for the slope. So if you were to be given a potential energy versus position graph, okay, so potential energy versus position, you can say that this is J. It is correct to say, let's say we were given something that looks like this, right? It is correct to say that the slope is the force. Okay? The slope is the force, or the negative of that, the negative value of it will be the force of a potential energy versus position type of graph. And so what that tells us is how much force is required to change the potential energy as it moves from one state to another. And if we were to go back to the dropping object, right? So if we were to go to this, and if we were to link this with F is equal to negative du dx, we can say that as this object is falling, its potential energy is changing. Now let's remind yourselves, gravitational potential energy is mgh. Right? So as the height is decreasing, as your height is approaching 0, you're losing potential energy. Right? So that means your du is getting smaller, right? There's it's changing by a certain amount. And so as it's decreasing in height, the potential energy changes. And what changes that potential energy? Why? It's that force. Okay? And that's where that F comes from. The force will drag this object to the earth, and therefore the potential energy will change based on how much the position is changing. So we just used this equation to describe the scenario. And these graphs are used, so I just drew any kind of line, right? You could be given that kind of line, you can be given like a line that looks like this, right? Whatever the line is the potential energy, the graphs. And you can find the slope of that line, and that slope will tell you how much force is being used to just change the potential energy. Alrighty, I'll see you next time. Bye-bye.